Welcome to finding volume with washers. So the general idea is when we rotate a region about an axis, its cross sections do not have to be solid disks. So its cross sections do not have to be solid disks. Instead, they can have holes in the middle. So instead, the cross sections can be disks with holes in the middle. And we call these washers. So just sort of for a basic visual, if we take some squiggle above the x-axis, and then let's take, say, a horizontal line between the x-axis and that squiggle. And then we are wanting to rotate the region that's above the horizontal line and below our squiggle between A and B about the axis, x-axis. So when we rotate about the x-axis, we will not have anything in that little middle of our shape since we are rotating empty space there. So we will wind up with our squiggle gets fully rotated around. And then the inside line gets fully rotated around. And we essentially have a long donut, basically, with a hole through the middle. And so our cross sections here will be our washers. So the cross sections look like a flat washer, like what you use with a screw. So again, our cross sections are a disc with a hole in the middle. Let me draw that vertically instead of horizontally. So in order to find this volume, you can just do the big disk minus the missing middle piece. So note the washer volume is just the large disk minus the hole, essentially. So the rule says essentially that our dV, so our washer volume, we are looking at dV is equal to, we do our large disk, pi times capital R squared, and then times dx minus pi times lowercase r squared dx, otherwise known as pi times capital R squared minus lowercase r squared all times dx. So the formula we were using here, that pi times capital R squared times dx, this is our volume of the large disk. The pi times lowercase r squared times dx is the volume of the whole. And so this is where our formula comes from for our dV. Here, capital R is the large radius. Lowercase r is the radius of the hole. So the small radius or radius of the hole. And so we get our overall volume is just equal to the definite integral from a to b of pi times capital R squared minus lowercase r squared, all of that times pi, times dx. So let's go ahead and just do one example here. We'll see more examples in the next video. Let's find the volume of the rotational solid formed by rotating the below shaded region about the x-axis. I realized I did not shade here. The region that we are wanting to rotate is the region that is above tangent of x and below y equals 1, that is also to the right of the y-axis. So we are wanting to rotate this about the x-axis. So if we rotate about the x-axis, the shape we wind up getting looks like we draw our original shape. We're rotating about the x-axis, so we can draw its sort of mirror image across the x-axis, below the x-axis. And then we're rotating, so we just get a bunch of cylinders. So the large cylinder is just flat across at y equals 1. The interior holes are the ones that will look different. So our interior holes will follow along that tangent of x. So we get kind of a reverse funnel. Essentially, we have a cylinder missing a funnel, right? So note that if we're looking at tan x between y equals 0 and 1, so I should say we're looking at y equals tan x between y equals 0 and 1. So that means that x is between x equals tan inverse of 0 and tan inverse of 1. So that's x is between 0 and pi over 4. So we are looking for x values between 0 and pi over 4. We have our outer radius and our inner radius. So our outer radius or our large radius we are just looking at that entire distance from the x-axis to 1. So our capital R of x is just 1 minus 0, otherwise known as 1. That large radius is a constant 1. Our inner radius, or our small radius, R of x, that small radius is running from the x-axis to tangent of x. So this is just tangent of x minus 0, otherwise known as tangent of x. So our washer volume we are looking at, I'm going to move that to the next page, sorry. Our washer volume, we are looking at dV is equal to pi times capital R squared minus lowercase r squared dx. So dV is equal to pi times 1 squared minus tangent squared of x dx. So our total volume we put all of these together. We have our volume is, we're doing in terms of dx, so we should run in terms of x from 0 to pi over 4. So we're using dx. So that means the bounds are in x. So we're running from 0 to 4, and then of course our dV was pi times 1 minus tan squared of x dx. So we are looking at our volume as the integral from 0 to pi over 4. Our volume is pi times the integral from 0 to pi over 4 of 1 minus tangent squared of x dx. Once again, we will go ahead and use the fact that tangent squared of x is secant squared of x minus 1. So we are looking at pi times the integral from 0 to pi over 4 of 1 minus, in parentheses, secant squared x minus 1 dx, otherwise known as pi times the definite integral from 0 to pi over 4 of 2 minus secant squared of x dx. So this becomes pi times, in parentheses, 2x minus tangent of x. We are evaluating at 0 and pi over 4. This is pi times, we have a 2 times pi over 4 minus tangent of pi over 4. And we subtract off 2 times 0 minus tangent of 0. Once again, tangent of 0 is just 0. Tangent of pi over 4 is 1. So we are looking at pi times pi over 2 minus 1, otherwise known as pi squared over 2 minus pi, or pi squared minus 2 pi all over 2. So this was finding volume, again, using washers. We will do more examples in the next video.